All right, let's continue. Stochastic gradient descent. Do you remember the way that Arthur Samuel described machine learning, which we quoted in chapter 1? Suppose we arrange for some automatic means of testing the effectiveness of any current weight assignment in terms of actual performance and provide a mechanism for altering the weight assignments so that as to maximize the performance. We need not go into the details of such a procedure to see that it could be made entirely automatic and to see that a machine so programmed would learn from an experience. As we discussed, this is the key to allowing us to have a model that can get better and better, that can learn, but our pixel similarity approach does not really do this. We do not have any kind of weight assignment or any way of improving based on testing the effectiveness of a weight assignment. In other words, we can't really improve our pixel similarity approach by modifying a set of parameters. To take advantage of the power of deep learning, we will first have to represent our task in the way that Samuel described it. Instead of trying to find the similarity between an image and an ideal image, we could instead look at each individual pixel and come up with a set of weights for each, such that the highest weights are associated with those pixels most likely to be black for a particular category. For instance, pixels towards the bottom right are not very likely to be activated for a 7, so they should have a low weight for a 7, but they are likely to be activated for an 8, so they should have a high weight for an 8. This can be represented as a function and a set of weight values for each possible category. For instance, the probability of being the number 8 can be represented by this function called PR8, so probability 8, given two arguments, xw, where x I assume is the input and w is the weight matrices. So you kind of want this resulting tensor of multiplying the input by the weights and summing it up to be high if it's really an 8, and then low if it's not an 8. Okay, so here we are assuming that x is the image represented as a vector. In other words, with all the rows stacked up end to end in a long line. And we are assuming that the weights are a vector w. If we have this function, we just need some way to update the weights to make them a little bit better. With such an approach, we can repeat that step a number of times, making the weights better and better until they are as good as we can make them. We want to find the specific values for the vector w that cause the result of our function to be high for those images that are 8s, and low for those images that are not. Searching for the best vector w is a way to search for the best function for recognizing 8s. Because we are not yet using a deep neural network, we are limited by what our function can do. We are going to fix that constraint later in this chapter. To be more specific, here are the steps required to turn this function into a machine learning classifier. First, initialize the weights, so some arbitrary weight vector or matrix. Then for each image, use these weights to predict whether it appears to be a 3 or a 7. So we do like the whole PR8 thing, but now it's going to be like PR3, PR7. And we'll just multiply the input by those weights, and then we take the sum. And if it's a high one where it's like we expect it to be a 7, 7 would be high. Anything else would be low. Same thing for like the 3s. Based on these predictions, calculate how good the model is, so its loss. Then calculate the gradient, which measures for each weight how changing that weight might change the loss. Then we step, that is, change all the weights based on that calculation. Then go back to step 2 and repeat the process. Then you iterate until you decide to stop the training process. For instance, because the model is good enough or you don't want to wait any longer. So one thing to keep in mind is that when it comes to training models, there's never a done. It's only when you feel like the results are good enough for you. Now, the gradient here is measures for each weight. So each element in that W vector, if you change that specific weight, how much would it change the loss? And the loss is basically the predictions of the difference between the predictions and the target, so the ground truth. So if you were to change the weight value, how would it affect this loss right here? And the goal is to get this loss smaller. So you want to change the weight in a way that this becomes a smaller number. And how much to change that weight is going to be something called the gradient. The gradient is like how much do you need to change that weight to get this loss to be smaller. Okay, and then you repeat this process. So you initialize. Let me read all of this first. So these 7 steps illustrated in Figure 4-1 are the key to the training of all deep learning models. That deep learning turns out to rely entirely on these steps is extremely surprising and counterintuitive. It's amazing that this process can solve such complex problems, but as you'll see, it really does. So we initialize random weights, we predict given those weights and input, calculate the loss, then calculate the gradient, and then step to adjust the weights. And then we just repeat until we want to stop. So there are many ways to do each of these 7 steps, and we'll be learning about them throughout the rest of this book. These are the details that make a big difference for deep learning practitioners, but it turns out that the general approach to each one follows some basic principles. Here are the guidelines. So first we want to initialize. We initialize the parameters to random values. This may sound surprising. There are certainly other choices we could make, such as initializing them to the percentage of times that the pixel is activated for that category. But since we already know that we have a routine to improve these weights, it turns out that just starting with random weights works perfectly well. Then there's loss. This is what Samuel referred to when he spoke of testing the effectiveness of any current weight assignment in terms of actual performance. We need a function that will return a number that is small if the performance of the model is good. The standard approach is to treat a small loss as good and a large loss as bad, although this is just a convention. Step. A simple way to figure out whether a weight should be increased a bit or decreased a bit would be just to try it. Increase the weight by a small amount and see if the loss goes up or down. Once you find the correct direction, you could change that amount by a bit more or a bit less until you find an amount that works well. So it is possible to train a model without any calculus or like gradient calculation. You just have to like guess your way through and just like do little small like adjustments. But it's slow. As we will see, the magic of calculus allows us to directly figure out which direction and by roughly how much to change each weight without having to try all these small changes. The way to do this is by calculating the gradients. This is just a performance optimization. We would get exactly the same results by using the slower manual process as well. Stop. Once we decided how many epochs to train the model for, a few suggestions were given earlier in this list. We apply that decision for our digit classifier. We would keep training until the accuracy of the model started getting worse or we ran out of time. Before applying these steps to our image classification problem, let's illustrate what they look like in a simpler case. First, we will try to define a very simple function, the quadratic. Let's pretend that this is our loss function and x is a weight parameter of the function. Okay, so the quadratic is our loss function, so that's how what we're going to use to compute the loss, and x is the weight, one of those weight parameters for that function. So it's a one parameter model. So here's a graph of that function. Okay, here we go. Okay, and then it's a parameter. And the sequence of steps we described earlier starts by picking a random value for a parameter and then calculating the value of that loss. So let's pick any random value for the parameter and then calculate the value for the loss. Okay, so any parameter, negative 1.5. So that's going to be here. Okay. Now we look to see what would happen if we increase or decrease our parameter by a little bit, the adjustment. This is simply the slope at a particular point. Okay, so we picked a new parameter and we found to be going down. So we can change our weight by a little in the direction of the slope, calculate our loss and adjustment again, and then repeat this a few times. Eventually we will get to the lowest point in our curve. Okay, this basic idea goes all the way back to Isaac Newton, who pointed out that we can optimize arbitrary functions in this way. Regardless of how complicated our functions become, this basic approach of gradient descent will not significantly change. The only minor changes we will see later in this book are some handy ways we can make it faster by finding better steps. So calculating gradients. The one magic step is a bit where we calculate the gradients. As we mentioned, we use calculus as a performance optimization. It allows us to more quickly calculate whether our loss will go up or down when we adjust our parameters up or down. And in other words, the gradients will tell us how much we have to change each weight to make our model better. So you may remember from your high school calculus class that the derivative of a function tells you how much a change in its parameters will change its results. So the derivative of a function, so given some function, a derivative is basically how much change do you need to make to change its result in a certain amount. So by specifying or passing or finding the derivative of a function at a certain spot, you'll know that based off of that value, it's going to change your result by a certain amount. So if not, don't worry. Let lots of us forget calculus once high school is behind us, but you will need some intuitive understanding of what a derivative is before you continue. So this is all very fuzzy in your head. Head over to Khan Academy and complete the lessons on basic derivatives. You won't have to know how to calculate them yourself, but you just need to know what a derivative is. The key point about a derivative is this. For any function, such as the quadratic function we saw in the previous section, we calculate its derivative. The derivative is another function. It calculates the change rather than the value. Okay, so the derivative is another function, and given some sort of result of that function, it will tell you the change at that point rather than the value. For instance, the derivative of the quadratic function at the value 3 tells us how rapidly the function changes at the value 3. More specifically, you may recall that the gradient is defined as rise over run. That is the change in the value of the function divided by the change in the value of the parameter. When we know how our function will change, we will know what we need to do to make it smaller. This is the key to machine learning, having a way to change the parameters of a function to make it smaller. Calculus provides us with a computational shortcut, the derivative, which lets us directly calculate the gradients of our function. One important thing to be aware of is that our function has lots of weights that we need to adjust. So when we calculate the derivative, we won't get back one number, but lots of them, a gradient for every weight. But there's nothing mathematically tricky here. You can calculate the derivative with respect to one weight and treat all the other ones as constant. And that's a partial derivative, and then repeat that for every other weight. This is how all of the gradients are calculated for every weight. We mentioned just now that you won't have to calculate any gradients yourself. How can that be? Amazingly enough, PyTorch is able to automatically compute the derivative of nearly any function. What's more is that it does it very fast. Most of the time, it will be at least as fast as any derivative function that you can create by hand. Let's see an example. First, let's pick a tensor value at which we want gradients. So we're going to create a tensor of 3, and then requires grad method still returns back a tensor. It just sets this tensor to probably, like this tensor object by PyTorch, to have gradients or keep track of gradients. Notice a special method requires grad. That's a magical incantation we use to tell PyTorch that we want to calculate gradients with respect to that variable at that value. It is essentially tagging the variable so the PyTorch will remember to keep track of how to compute gradients of the other direct calculations on it that you will ask for. Okay, so it kind of like registers the specific tensor into some sort of, I guess, compute uh, graph or list, so that when something happens, it just goes back and kind of updates that specific tensor. So this API might throw you off if you're coming from a math or physics background, I guess. In those contexts, the gradient of a function is just another function, its derivative. So you might expect gradient-related APIs to give you a new function. But in deep learning, gradient usually means the value of a function's derivative at a particular argument value. The PyTorch API also puts the focus on the argument, not the function you're actually computing the gradients of. It may feel backwards at first, but it's just a different perspective. Okay, so let's read that again. In deep learning, a gradient usually means the value of a function's derivative at a particular argument value. So I think PyTorch is keeping track of the numeric value, not like the function derivative. It's the value at a specific point. Okay. So now we calculate our function with that value. Notice how PyTorch prints not just the value calculated, but also note that it has a gradient function it'll be using to calculate our gradients when needed. So, whoa, where did we go? Okay, here we go. So yt equals fx of t. And this is, I think, still our parabolic function. So then given that we had 3 as the argument, of course, x squared is going to result in 9. And we do have a gradient function, pow backward, I guess. Finally, we tell PyTorch to calculate the gradients for us, yt.backward. That's backward method. The backward here refers to backpropagation, which is the name given to the process of calculating the derivative of each layer. We'll see how this is done exactly in chapter 17. When we calculate the gradients of a deep neural net from scratch, this is called the backward pass of the network, as opposed to the forward pass, which is where the activations are calculated. Life would probably be much easier if backward was just called calculate grad, but deep learning folks really do like to add jargon everywhere they can. So we can now view the gradients by checking the grad attribute of our tensor, xt.grad. So again, we can view the gradients. So the resulting value by applying your argument value to its derivative function. So in this case, the derivative was x squared, or sorry, the function was x squared. Taking the derivative is 2x. Yeah, it's 2x. And then multiply that by 3, you get 6. So if you remember your high school calculus rules, the derivative of x squared is 2x, and we have x equals 3. So the gradients should be 2 times 3 equals 6, which is what PyTorch calculated for us. So now we'll repeat the preceding steps, but with a vector argument for our function. So okay, now instead of passing a scalar 3, we're going to be passing in a tensor, a 1D tensor, a vector. So it's 3, 4, 10. And we just register that with requires grad. And so when we compute fxt, xt being this tensor here, we will get what? 9, 16, 100. Then we take the sum, we get one tensor, 125. And then we have a gradient function called sum backward 0. And so I wonder how it figures that out, actually. Like, how does it know the specific one? I think it's because each of these operations probably have implemented their own backwards function. Oh yeah, that makes sense. Okay, so like basically depending on like how you got this tensor based off of this method, there's like a specific backwards function that's associated here, and that's how the gradient function is probably determined. We need to read more about PyTorch. So this is probably a to-do after this book. Okay, anyway. So let's say we got this result here. It's a 125. Now we do yt backward. Well, x squared, 2x. 2x is going to be what? X is going to be vector. So 3, 4, 10. 2x is going to be 6. 6, 8, 20. Okay, cool. Um, 6, 8, 20. Okay, so the gradients tell us only the slope of our function. They don't tell us exactly how far to adjust the parameters. So, but they do give us some idea of how far. If the slope is very large, that may suggest that we have more adjustments to do, whereas if the slope is very small, that may suggest that we are very close to the optimal value. Stepping with the learning rate. Deciding how to change our parameters based on the values of the gradients is an important part of the deep learning process. Nearly all approaches, I keep saying approaches, nearly all approaches start with the basic idea of multiplying the gradient by some small number called the learning rate, LR. The learning rate is often a number between 0.001 and 0.1, although it can be anything. Often people select their learning rate just by trying a few and finding which results in the best model after training. We'll show you a better approach later in this book called the Learning Rate Finder. Once you've picked the learning rate, you can adjust your parameters using this simple function. W grad times LR and then minus this result from the weight parameters. So for every parameter in your weight, you're going to just take each corresponding gradient value, multiplying that by the learning rate, and then just subtracting it from the current. So this is known as stepping your parameters using an optimization step. If you pick the learning rate that's too low, it can mean having to do a lot of steps like this, because you're adjusting very, very small. But picking a learning rate that's too high is even worse. It can result in the loss getting worse, as we see in figure 4-3. So you just completely miss things. If the learning rate is too high, it may also bounce around rather than diverging. Okay, so it shows the results in taking too many steps to train successfully. And now let's apply all this in an end-to-end example. An end-to-end SGD example. We've seen how to use gradients to minimize our loss. Now it's time to look at an SGD example and see how finding a minimum can be used to train a model to fit data better. So let's start with a simple synthetic example model. Imagine you were measuring the speed of a roller coaster as it went over the top of a hump. It would start fast and then get slower as it went up the hill. It would be slowest at the top, and it would then speed up again as it went downhill. You want to build a model of how the speed changes over time. If you were measuring the speed manually every second for 20 seconds, it might look something like this. So this is going to be an input tensor. So what is it? The speed manually for 20 seconds. Oh no, this is the time. Okay, this is the time, and then this is the speed. All right, cool. Okay. So this is how you model the speed. Got it. All right, so it becomes like this. So here we're probably at the top with the roller coaster. Okay, so we've added a bit of random noise. Since measuring things manually isn't precise, this means that it's not that easy to answer the question. What was the roller coaster speed? Using SGD, we can try to find a function that matches our observations. We can't consider every possible function, so let's use a guess that it will be quadratic. An example, a function of the form a times squared times b times time plus c. We want to distinguish clearly between the function's input, the time when we are measuring the coaster speed, and its parameters, the values that define which quadratic we're trying. So let's collect the parameters in one argument and thus separate the input t and the parameters params in the function signature. Okay, so these will be the parameters, and then I guess this will be t. Okay, so they're going to, okay, so yeah, so parameters is going to be ABC, and then, so given these params, we just compute this function here. So in other words, we've restricted the problem of finding the best imaginable function that fits the data to finding the best quadratic function. Okay, this greatly simplifies the problem since every quadratic function is fully defined by 3 parameters, a, b, and c. Thus, to find the best quadratic formula, we just need to only find the best values for a, b, c. If we can solve this problem for 3 parameters of a quadratic function, we'll be able to apply the same approach for other more complex functions with more parameters, such as a neural net. Let's find the parameters for f first, and then we'll come back to do the same thing for the MNIST data set with the neural net. We need to define first what we mean by best. We define this precisely by choosing a loss function, which we will return a value based on the prediction and a target, where lower values of the function correspond to better predictions. For continuous data, it's common to use mean squared error. Okay, so predictions minus targets squared, so these are vectors. You square all the values, then you take the mean. So now let's work through our 7-step process. So for step 1, to do our roller coaster model, we had to first initialize the parameters A, B, C to be random values. Okay, so random value tensor, make sure it requires grad. Then we calculate the predictions, and it's going to be nonsense in the beginning with our time vector. So given that time 1, time 2, we just need to predict the speed at all those points in time. So then once we do that, let's plot them with this show preds. So let's create a little function to see how close our predictions are to our target and take a look. Okay, so I think this is the red one, right? The red one, yeah, color red. Okay, so it looks like it's just getting slow. This doesn't look very close. Our random parameters suggest that the roller coaster will end up going backwards since we have negative speeds. We calculate the loss as follows. Loss is MSE pred speed. Then we get this big number as a tensor, so that's our loss. So our goal is now to improve this. To do that, we'll need to know the gradients. So step 4, calculate the gradients. Next step is to calculate the gradients, or an approximation of how the parameters need to change. So we take the loss dot backwards, so that's it's being tracked. Then we see what our gradients are for those parameters. Okay, and then we take that value, multiply that by the learning rate, and this results in how much we need to subtract away from our current parameters. I believe if we go back up to here, right? So you multiply the gradient vector times the learning rate, and then you just subtract it from your weights. So I think we just need to subtract it from the params vector. And so okay, so we can use these gradients to improve our parameters. We'll need to pick a learning rate. We'll discuss how to do that in practice in the next chapter. For now, we'll just use 1e negative 5. Params, okay, we get this. And then we need to step the weights. So we just need to, well, we already did this whole multiplication thing. Okay, sure. We'll just apply that, and then we'll reset the gradient for the next pass, I believe. Yeah. So understanding this bit depends on remembering recent history. To calculate the gradients, we call backward on the loss, but this loss itself was calculated by MSC, which in turn took preds as an input, which was then calculated using f taking as an input params, which was the object on which we originally called required grads, which is the original call that now allows us to call backward on loss. This chain of function call represents the mathematical composition of functions, which enables PyTorch to use calculus's chain rule underneath the hood to calculate these gradients. Okay, so let's see if the loss has improved by just that one step. Yes, because MSC is a lot smaller now. And taking a look at the plot, it's kind of like flattened out a little bit. So then you repeat this a few times by wrapping all the operations that we did earlier into a function called apply step, where we take the predictions, we calculate the loss through MSE, then we propagate backwards, we adjust the params by multiplying the learning rate with the gradients, and then we reset the gradients, and then there we go. So we repeat the process, we go through 10 steps. So eventually converges to 676-ish. So now we iterate by looping and performing many improvements. We hope to reach a good result. Okay, so it does go down pretty well. Like, yeah, not linearly. It just goes down really quick and then slows down. So the loss is going down just as we had hoped, but looking at these loss numbers disguises the fact that each iteration represents an entirely different quadratic function being tried on the way to finding the best possible quadratic function. We can see this process visually if instead of printing out the loss function, we plot the function at every step. Then we can show how the shape is approaching the best possible quadratic function for our data. Okay. We decided to stop just after 10 epochs arbitrarily. In practice, we will watch the training and validation losses in our metrics to decide when to stop, as we've discussed. Summarizing gradient descent. Now that you've seen what happens in each step, let's take another look at our graphical representation of the gradient descent process and do a quick recap. Okay, again, initialize the parameters, then you run prediction, you get the loss, then you find the gradient for the loss, then you step to adjust your parameters based off of what you found from those gradients and multiplied by your learning rate, and then just adjusting your parameters with that value. So at the beginning, the weights of our model can be random, training from scratch or coming from a pre-trained model, transfer learning, or fine-tuning, I guess. In the first case, the output we will get from our inputs won't have anything to do with what we want. And even in the second case, it's likely that the pre-trained model won't be very good at the specific task we are targeting. So the model will need to learn better weights. We begin by comparing the outputs that the model gives us with our targets. We have labeled data so we know what result the model should give using a loss function, which returns a number that we want to make as low as possible by improving our weights. To do this, we take a few data items such as images from the training set and feed them to our model. We compare the corresponding topics we compare the corresponding targets using our loss function, and the score we get tells us how wrong our predictions were. Okay, we compare the corresponding targets, so that's the ground truth, using our loss functions, and the score, the result of that loss function, tells us how wrong our predictions were. So bigger loss, more wrong. We then change the weights a little bit to make it slightly better. To find out how to change the weights to make the loss a bit better, we use calculus to calculate the gradients. Actually, we let PyTorch do it for us. Let's consider an analogy. Imagine you are lost in the mountains with your car parked at the lowest point. To find your way back to it, you might wander in a random direction. But that probably won't help too much, since you know your vehicle is at the lowest point. You would be better off going downhill by always taking a step in the direction of the steepest downward slope. You should eventually arrive at your destination. We use the magnitude of the gradient, the steepness of the slope, to tell us how big of a step to take. Okay, specifically, we multiply the gradient by the number we choose called the learning rate to decide on the step size. Then we iterate until we have reached the lowest point, which will be our parking lot, and then we can stop. All of what we just saw can be transposed directly to the MNIST dataset except for the loss function. Let's see how we can define a good training objective. The MNIST loss function. We already have our XS, that is, our independent variable, X's, XS, that is our independent variables, the image themselves. We'll concatenate them all into a single tensor and also change them from a list of matrices, a rank 3 tensor, to a list of vectors, a rank 2 tensor. We can do this using view, which is the PyTorch method that changes the shape of a tensor without changing its contents. -1 is a special parameter to view that means make this axis as big as necessary to fit all the data. So train X is going to be torch.cat stacked 3s and stacked 7s. We want to just turn it into one big list of 28 by 28. Is that so? let's see. So stack 3's at this point is what? Okay, let's check it out. So stacked 3's is going to be 3-dimensional. And if we torch.cat, so catted torch.cat, in this case, a list of tensors we want to process is stacked 3's and stacked 7's. What do we get? Okay, catted. Okay, so here it's the same thing. It's just probably concatenating both the stacked 3's and stacked 7's together. Okay, so that's also going to be 3-dimensional. And it looks like here, it's just like a, let's do a dot shape. Catted dot shape. Okay, it just looks like it's a bunch of these and it's 28 by 28. So both the images combined in terms of concatenated list of 28 by 28 images, just thinking aloud. And if we do dot view, -1, 28 by 28, what do we get? So catted equals catted dot view -1, 28, 28. And then let's just say catted view. And then catted view here is 1. So it's still 3-dimension, right? Let's see. Catted view dot shape. Yeah, it's still the same thing. Why is that? Let's see. Oh, 28 times 28. Sorry. 28 times 28. Oh, okay. So I get it now. What we're trying to do is we're trying to take that image and catted view. Yeah, catted view. We're trying to take this image and flatten out the 28 by 28 into one-dimensional vector, like I said. Okay, makes sense now. And so now we only have 2 dimensions because we have, in this case, was it 12,396 images of these things, and it'll be 28 times 28 worth. I don't know why it doesn't show us the real size. Is it because it doesn't change the size of the underlying tensor? It just like gives us back like, what is it? I guess really just a view, like an interpretation. Okay. I'll take that, I guess. So we'll call this train X instead of catted view. We'll do train X, and then train X dot shape will help. Oops, there you go. And I think we want to do train Y too, which is just going to be, I don't know what this unsqueeze is. I forgot already. Is that to like reduce the dimensions? Let's see. Train Y is going to be, so it's going to take 1, right? This simple list, and it's going to be converted to a vector. We're going to repeat that for 6,000 something times, and then we're going to I guess concatenate that with 0 with another 6,000 times corresponding to 7's. And I guess we're going to try and classify the 3, so we want to match the 3's in this case, and these are the labels. That makes sense. So it's either a 3 or a 7, and it's a 1. If it's a 1, it'll be a 3. If it's a 0, it'll be a 7. And each element here in train X corresponds to this element in train Y. And squeeze is interesting. So let's just do this one at a time. So we're going to create a tensor, a big tensor. Train Y temp, it's going to be torch.tensor 1 times the length of 3's, and then we're going to concatenate that with the length of 7 zeros, and then let's do train y temp dot shape, and that's just a linear one, okay? But then if we unsqueeze, so train y equals to train y temp dot unsqueeze -1, okay, train y dot shape. Oh, okay, so we just turn to 2 dimensions. Oh, okay. So it's going to be 12,396 elements of a single, like a vector with a single element, either a 0 or 1 inside. Okay. So it'll look something like this. Either 1, 0, 0, and so on. Those are the training labels. Okay. So far so good. That totally makes sense. Then we're gonna output the shapes here. So train x dot shape, train y dot shape. Okay. At this point, then I should have had the right train x. Yeah, I do. Okay, great. Oh, I know why this is still wrong, because I didn't rerun it. Silly me. Already a long day. Okay. So a dataset in PyTorch is required to return a tuple of x, y when indexed. Python provides a zip function to do that. When combined with list, provides a simple way to get this functionality. So we're going to create a corresponding of every element in train x to train y, it looks like. So the input and in the label. So data set here is just going to be a list of these things. So it'll be, in this case, a list where one element is going to correspond with a list of 784 elements. Okay. And then another list that is only one element, either 0 or 1. Okay. And that's true right here. And then what we want to do is we want to create a validation set. So yeah, we just do the same thing with the valid 3's and the valid 7 tensors. Okay. I'm not sure. Did we even create that? It's already section. I've divided this chapter reading to too many parts that I can't remember anymore. But let's just do that. Let's create a data set. Should be pretty easy. Okay, so easy enough to write that. Dset is going to be list zip train x, train y. And let's just output dset. Oh no, we do not want to output dset. Dset.length. So len dset. Okay. Okay, so we have this many elements. And let's just output, I guess, the first element dot shape, and then the second element dot shape. Oh, it's converted already. So len okay, cool. All 2. Length of this is 2, I guess. Oh wait, it's a list of a list. So this will be 0, 0. So I've been working today. Okay, that makes sense. Okay, now we're going to have to create So we have the data set. Now we have to create a validation set for X and Y. Same way. Create that data set. Okay. Let's do it. So valid X is going to be torch dot cat list of tensors, valid 3 tens, valid 7 tens, and then what do? We do dot view -1, 28 times 28 in this case, and then valid Y is going to be torch dot tens, and that's going to be 1 times valid 3s, I guess, then valid 3 dist. What's dist? Or whatever. Valid 3 tens times 0 times then a valid 7 tens. Okay. And I think we unsqueeze this one. So we want to add another dimension to the tensor. Okay, and then let's just output the shape to see we're in good shape. Tensor, sorry. Tensor. Can't multiply. Oops, plus. Okay. Makes sense. Now we create that data set. So valid D set. Is that what we're going to call it? Valid D set, yes. Valid D set is going to be, in this case, list zip valid X, valid Y. And again, valid D set, I guess 0 dot 0 dot shape valid D set 0 1 dot shape. Great. Okay, next step. Now we need an initially random weight for every pixel. This is the initialize step in our 7-step process. So we're going to initialize weight matrix. Def init params. The size is going to be 784. I don't know what STD is, but it's just to help with the randomness. Return a tensor that is 784 random numbers. I guess a standard deviation. Make sure it has requires grad so that it's part of that back propagation thing. Okay, let's try that. Def init params size SED is going to be 1.0, and then we want to return torch.randn. And what's this? Size. So it's going to be size times, I guess, std. And then, is that it? Dot requires grad. Or requires grad. There we go. I don't know what's with the underscore. Okay. Then we just need to initialize our weights. So weights equals to init params. 28 times 28, 1, and then weights dot shape. Okay. It is a 784 element tensor. So the function weights times pixels won't be flexible enough. It is always equal to 0 when the pixels are equal to 0. An example, its intercept is 0. You might remember from high school math that the formula for a line is y equals w times x plus b. So we still need the b. We'll initialize it to a random number 2. So all the bias. So bias is just one of these. So a tensor of one element, init params 1. Okay, so bias is going to be init params of 1. So this is also a tensor too. It's just a one element tensor. And I can show that right here. Wait, why? Must be a tuple of ints, but found an element of type float at position 0. Wait, what? Wait, I did something wrong. 28 to 28. But that was correct. Let's see. Bias. We'll return back a tensor. Do we get anything here? No. Argument of size must at position 1 must be a tuple of ints but found element of type float. But I already... Oh. Is that so? That makes sense. Okay, so it has to be an integer. Alright. So that is a random number. Okay, so that's what we're going to have to train. This and this is what we have to train. In neural networks, the W in the equation, Wx plus B, is called the weight. So for every element in W, we multiply for every element in X. Then we just add B. And B is called the bias. Together, the weights and the bias make up the parameters. Okay, so jargon, parameters, the weights and biases of a model. The weights are the W in the equation W times X plus B. And the biases are the B in that equation. So we can now calculate a prediction for one image. Yes, okay. So train X as 0. So take one of the images, multiply it by the weights transposed, and then take the sum plus the bias. Then we get this number here. Okay. I can't tell whether or not that's good or bad. So while we could use a Python loop, for loop to calculate the prediction for each image, that would be very slow because Python loops don't run on the GPU, and because Python is a slow language for loops in general, we need to represent as much of the computation in the model as possible using higher level functions. In this case, there's an extremely convenient mathematical operation that calculates W times X for every row of a matrix called matrix multiplication. So figure 4-6 shows what matrix multiplication looks like. So it's like multiply every row by every column of the second matrix, basically. And that becomes a scalar, and that becomes an element at that position for the new matrix. This image shows two matrices A and B being multiplied together. Each item of the result. Oh, and when we say multiply, it's like taking the dot product. Taking the dot product of every row in the first matrix with every column of that corresponding column in the second matrix. And then that dot product becomes a new element. Okay. Each item of the result, which we'll call AB, contains each item of its corresponding row of A multiplied by each item of its corresponding column of B added together. For instance, row 1, column 2, the yellow dot with the red border is calculated as A1 times A11 times B12 plus A12 times B22. If you need a refresher on matrix multiplication, we suggest you take a look at the Intro to Matrix Multiplication on Khan Academy, since this is the most important mathematical operation in deep learning. It is true. It's the most important one. So in Python, matrix multiplication is represented with the @ operator. So let's try that. And then we're going to create a linear function that will just take, I guess, the input, xb. I don't know what b means. Okay. So xb multiplied matrix multiply weights plus bias, return that, and that's our prediction. So we're going to predict for every single image that number. Okay, let's do it. Def linear. Is it linear 1 or linear? Linear 1. I'm guessing he's going to optimize. xb, return xb at weights plus bias. And then we are just going to go through all of them. Preds is linear 1 train x. Preds equals linear 1 train x. So we're going to create another vector that has all the predictions. So preds.shape. Okay, so in preds, let's just kind of output the first 5 maybe. There we go. So these are the first 5 results. Or not the first 5, this is the first 5. There you go. Okay. Oh, okay, so for me, it's negative 1.7715. And then that's correct. Cool. So the first 5 here are correct, I'm assuming. Okay. The first element is the same as we calculated before, as we expect. The equation batch. Oh, okay, batch, x batch. Okay. Batch at weights. So batch matrix multiply weights plus bias is one of the 2 fundamental questions of any neural network. The other one is the activation function, which we'll see in a moment. So let's check our accuracy. To decide if an output represents a 3 or a 7, we can just check whether it's greater than 0. So our accuracy for each item can be calculated using broadcasting. So no loops, as follows. Okay, so just basically check if everything is going to be greater than 0. We turn that into float, and then we're going to check to see if it's equal to the values that we got from train y. Okay, so basically we're going to have true for everything that is greater than 0, false for everything that is not. So this creates a new matrix or new tensor that has in every single element the result of this here. Okay, now if preds is greater than 0, that returns a boolean. We want to turn that into a float, so I'm guessing 1.0 or 0.0, and then this one is going to be, I guess, a 1 or 0. If you're checking for equals, then that will be true, and then you'll take the mean item. Okay. So corrects is going to be the preds greater than 0 dot float. We want to check to see if, well, we want to filter for everything, not filter, but like change every element to see whether or not it is equals to that corresponding element in train y. And then corrects, let's just check the first 5. That's not the first 5. Oh, wait, is it? That's not. Corrects. That's not correct. Train y. What did I do here? Preds float. Preds greater than 0.0. Float equals train y. Corrects. So let's just do corrects. So now we're in this situation where we have not the right shape. Why is that? Why is it a square? What did I do wrong here? So I went from 12396. Is this 12396 too? Is this even the right shape? Oh, we're supposed to init with the tuple. That may have been the problem. Okay. I think we still end up with relatively the same. Okay. Problem solved. Wait. So then this one is 1. Okay. Yeah. Okay, cool. Now let's see what the change in accuracy is for a small change in one of the weights. So this is kind of like changing with the learning rate. Yeah. So we're going to have to predict again. And so if weights equals or times equals 0. Was it 3 zeros? 2 zeros? 3 zeros? 3 zeros? 1. And then what do we have? The same predictions. And then we're just going to do everything we did earlier. So it will be Preds linear 1 train x again, and then preds greater than 0.0 dot float equals train y. I think we want to turn that into float mean item. Huh. What are we missing? Preds greater than 0.0 float equals train y, float mean item. Leaf variable that requires grads being used in an in-place operation. Oh, weights 0. Okay. A view of a leaf variable that requires grad is being used in an in-place operation. What does that mean? How does he do that? Huh. Is that how you do it? Why is that an issue? Okay, but we already have stuff. Is it because the Python changed? Let's look this up. A view of a leaf variable. Okay. Fastai. A view of a leaf variable is being used. Let's see how many people. Haha, weight 0 in place operation. Okay. Okay. Oh, it's errata. It's an error. Okay. Weights 0.data could also work. Okay, let's do weights 0.data. It seems more proper. Okay. So it changed just a little. It looks like, maybe. Maybe not. Maybe, maybe not. So weights dot shape, weights that. One reply. 4 hidden replies. Okay. Show all. Let's try this one. I have no clue. It's an error, so it's a mistake. Something should change, right? Maybe I should just read the bug. Yeah, this one changed. Did it? No, it didn't. Okay, let's just read on. I don't know, it's an error. Okay. So as we see, we need gradients to improve our... Wait, he might have gotten the same thing. Oh, he did. I just didn't read. As we see, we need gradients to improve our model using SGD. In order to calculate gradients, we need a loss function that represents how good our model is. That is because the gradients are a measure of how that loss function changes with small tweaks to the weights. So we need to choose our loss function. The obvious approach would be to use accuracy, which is our metric, as our loss function as well. In this case, we would calculate our prediction for each image, collect these values to calculate an overall accuracy, and then calculate the gradients of each weight with respect to that overall accuracy. Unfortunately, we have a significant technical problem here. The gradient of a function is its slope, or its steepness, which could be defined as rise over run, that is, how much of the value of the function goes up or down divided by how much we change the input. So we can write this mathematically as y new minus y old, x new minus x old. This gives a good approximation of the gradient when x new is very similar to x old, meaning that the difference is very small, but accuracy changes at all only when a prediction changes from a 3 to a 7 or vice versa. The problem is that a small change in weights from x old to x new isn't likely to cause any prediction to change. So y new minus y old will almost always be 0. In other words, the gradient is 0 almost everywhere. A very small change in the value of the weight will often not change the accuracy at all. This means it is not useful to use accuracy as a loss function. If we do, most of the time our gradients will be 0, and the model will not be able to learn from that number. Okay, so Sylvan says, in mathematical terms, accuracy is a function that is constant almost everywhere except at a threshold 0.5, so its derivative is nil almost everywhere and infinity at the threshold. This then gives gradients that are 0 or infinite, which are useless for updating the model. Okay, so instead of accuracy, so accuracy is not going to work. So instead, we need a loss function that when our weights result in slightly better predictions, gives us a slightly better loss. So what does a slightly better prediction look like exactly? Well, in this case, it means that if the correct answer is a 3, the score is a little higher, or the correct answer is a 7, the score is a little lower. Let's write such a function now. What form does it take? The loss function receives not the images themselves, but the predictions from the model. So let's make one argument preds of values between 0 and 1, or probabilities, predictions? I don't know. Where each value is the prediction of that image is a 3. Okay? It is a vector, rank 1 tensor indexed over the images.